Bro, my hair is getting out of control. What the heck, dude? And I do not dare tame this beast myself, okay? I'm starting to look like a lion, kind of. Actually, no, that would suggest that I'm, like, majestic looking now. I'm more like a woolly mammoth or something. What the heck is going on? Bro. But anyway, you're not here to watch me talk about my hair. You're here to see the first gold walkthrough of my life. Honestly, no idea how this is gonna go because I have not solved the gold problem since like 10th grade, okay? So we'll see how it goes. I mean, I solved like a couple platforms, but not many. At least, like recently, I've not solved anything. So let's see how this goes. Hopefully, I don't get too roasted, but we'll see. We'll see. Hello, everybody. I'm Karar, and today we are going to be doing USACO 3 on the past US Open Contest Gold. It's gonna be so epic. It's called exercise, so it has to be epic. Come on. Alrighty, Farmer John has come up with a new morning exercise routine for the cows again. As before, Farmer John's end cows are standing in a line. The I cow from the left has the label I. He then tells them to repeat the following step until the cows are in the same order as when they started. Okay, given a permutation A of length n, they change their order such that the I cow from the left before the change is AI from the left after the change. Okay, I kind of get it. Wait a minute, if you watch my permutation video, this sounds very similar, but it's probably harder. We'll see. What problem was that called again? I forgot what it was called. Whatever, moving on. For example, if A is equal to 1, 2, 3, 4, 5, then it becomes 2, 3, 1, 5, 4. How did that work? I do not get that. So, Okay. So in this case, it does go back to the same. Okay, that makes more sense. If A is 2, 3, 1, 5, 4, then the cows perform 6 steps. Okay, the order of the cows from left to right after each step is as follows. Okay, so 1, 2, 3, 4, 5, then it takes from the second one, and 3, 1, 2, 5, 4, 2, 3, 1, 4, 5. Okay. Find the sum of all positive k integers such that there exists a permutation of length n that requires the cow to take exactly k steps. As the number may be very large, output the number modulo m. Okay. So the modulo m doesn't matter, so we're basically just given n, and we want to find the sum of all positive integers k. And I'm assuming because n is less than 10 to the 4, we're just going to have to go through it one by one. Now, we did a really similar problem before. Like, I remember, I forgot, wait, is it wormhole sort? Yeah, it's probably wormhole sort or something. No, it was not wormhole sort. Whatever, okay. But basically, like, if you write out this permutation, 2, 3, 1, 5, 4, it's basically like you have 1, 2, 3, we draw a graph, right? And we label our nodes like this. Then in this case, the 2 goes into the 1. The third thing that's in the third place goes into the 2. The thing that's in the first place goes to the 3. Thing that's in the fifth place goes here, and then the thing that's in the fourth place goes here. And basically, the number of steps you gotta take is the least common multiple of all these different cycles, right? Because in order to get back to your original position, each cycle has to get back to its original position, right? Because in this case, like if you look over here, right, it goes 1, 2, 3, then this thing happens, right? So the 3 gets shifted over to the 2 gets shifted over to the 1, and the 1 gets shifted over to the 3. So you see in the first 3, right, like it repeats. So 1, 2, 3, 3, 1, 2, 2, 3, 1, and then again 1, 2, 3, 3, 1, 2, 2, 3, 1. So you can see that every time it's a multiple of the length of the cycle, which in this case the cycle is length 3. We got 1, 2, 3. It repeats every 3. So in order to get the whole thing to repeat, it has to be the least common multiple of all the different cycles that are present in it. And basically the sum of all these cycle lengths have to sum to n, right? Because this is 3, this is 2, they sum to 5. Okay. And we know that k is going to be the least common multiple of this thing. So we don't even need the cycles anymore, right? We just have to think about it like we had to divide n up into like a bunch of parts so that if we multiply the lengths of the parts together, they multiply to k. Or no, sorry, the LCM is k. So for example, if our n is equal to 5, we know we could get k is equal to 6 because we could split 5 into 3 and 2, which sum to 5, which is what we want, and they multiply to 6. So how do we find the sum of all positive integers that work? Well, okay, think about it this way, right? So if we take the prime factorization of a number, like let's say we have a number like k is equal to 8, we want to get k is equal to 8. Then we know that it's equal to 2 cubed, and then its factors are 1, 2, 4, 8. So what I was thinking is like, you first have to get the numbers to multiply to, or have an LCM of 8, right? Oh wait, yeah, we need an LCM of 8. So that means we at least need an 8 somewhere, because in an LCM you take the highest power that's present in any of the things, so we need an 8 somewhere. Let's try a different example. Let's try 24. 24 is equal to 2 cubed times 3 squared. So we know that one of our things has to be 8 and one of our things has to be 9 at least. But we want the smallest thing because if we want to increase our n without changing our k, we could just add a bunch of 1s, right? Because let's say our n is equal to 18, right? Right now, in order to get 24, we need an 8 and a 9, but that only sums to 17. What are we going to do? Oh no, we got to sum it to 18. So we just add a 1. So this sums to 18, but it still multiplies. Wait, am I trolling? Oh, whoops, this is a 3. So we need a 3. Let me change up my example entirely then. So it's 8 and 3, right? And let's say this is 12. So in order to get this to sum to 12 without changing what it multiplies to, we only had to add a 1. And now it still multiplies to 24, thus k is equal to 24 words. But we still get it summing to 12. So essentially what we had to do is we had to prime factorize our number, right? We get this thing over here. And then once we have this thing over here, we take the individual divisors, and we know that we have to have 1 8. We know we have to have a 3. If we had a 5 over here, we have to have 1 5. And we'll take the minimum thing, and then we can always add 1 if it's too small. But the only problem is that k could get pretty darn big. So how do we find it quickly? So if we're given n, we have to find ways to split it up. No, but this is so much faster. We have to be able to find the k's. How big could k be? Well, k could be literally n factorial though. Yeah, k could be pretty big. How do we know what k can be? But 10 to the 9 is pretty big. So we can't just go through all the modulo. No, but we gotta get the sum of them still. Oh wait, could we just do primes like log 2 and then, but then it'd be log 2 times log 2 of n times log 3 of n times, is that okay though? Huh. Oh, we gotta find a way to find the prime factors. Well, okay, so we know that if our answer is or if our n is 12, right? We know that 8 and all the things, all its divisors will work, right? Because all its divisors are guaranteed to have something like powers that are less than it. And we know that 8, the only thing we need is 8 times 1 times 1 times 1 times 1, and then we get 12. Could we do it using dp somehow? Okay, let's think about it this way, right? Maybe we could do dp like if dpij is like the sum of all the things where the biggest factor is 1. I is like biggest factor, okay. And then j is like how many leftover slots we have. So let's say that we just have a bunch of blanks, right? And we assume that they're all 1s. Then let's say that our n is equal to 5, and then I guess if we do dp2, then it would be 2, 2, 1. So so k would be 4. Oh no, k would be 2. Oh shoot, it's LCM. Oh, how do you find k? God dang, dude. God dang. I don't think this works though. Let's see. Oh, actually, wait. Leftover slots could be how much. It's yeah, j is n minus the sum. So how much space you have left over. So for dp2, we could have dp23 is equal to just 2 because you'd have 2, 1, 1, 1, and these are your leftovers. Or you just have 2, and then the rest are 1s, so there's 3 left over. And then dp1 would be equal to, or actually, why don't we just do how much it takes up? So it takes up 2. This one will, let's say, take up 4, and then if 2 is the biggest one, then we would have 4 here. Now, this is doesn't make sense. Right now this is kind of weird because this doesn't say anything, but once we get a 3 it gets interesting, I think. So to calculate dp3, we basically go through all the dp2s, right? And we're so dp2 0. So dp2 0, why don't we say is 1? And then we can multiply this 1 by 3, and then we'll have 3, and the leftover will be 2. And then we go through it 1 by 1. Oh, but we could also try to add 2 to this one and multiply this by 3 squared, but that doesn't work because that'll take us over 5, so no. Then and then we look at the next one, which would be dp2 1, but that's not possible because you can't have 2 as the biggest one and have a 1. So that doesn't work. So then you go on to dp2 2. Oh, this is so confusing, but I'm pretty sure this is the right way to do it. Okay, I need to hash this out properly. Okay, so let's just draw our grid. Let's say I over here, j over here, 1, 2, 3, 4, 5, 6, 7. So we know that 1s don't really matter, so we're just going to start at 2. And this is going to be, say, 0. 0, 1, 2, 3, 4, 5, 6. So for the max ones where 2 is the max number, there's no way to get it to 0 because you have to at least 1, 2, okay? So that's not going to work. For 1, it's not going to work. For 2, you could have 1, 2, so that works. So that's just going to be 2 because we're taking the sum of all the ones that work here. By the way, like, n is less than or equal to 10 to the 4th, so we could do n squared, so this should work if I could figure this out. And then 3 is impossible. 4, you could just have 2 2s, so that'll give you 4. 5 is impossible. Let's just say our n is equal to 6, so that we could go all the way to 6. Okay. And then impossible to get 5, and then 6 over here. Okay. Now for 3, if we wanted to get 0, that's impossible. If we wanted to get 1, that's impossible. If we wanted to get 2, wait, should it be if the max one is... No, I think I should be like, everything is like at most 3, so if it's 2, it should work too. But like these are still going to be zeros because we're going to consider the 1s as not counting. So in this case, we could have 2 over here because we just carry this over. And then for this one, we could just have 1, 3. For this one, we could, no, we can't get from over here, but we could get from over here. So this would be 4. And then here we could get from over here. Basically what I'm doing is I'm taking from previous ones and then we multiply by 3 to this one because we're adding a 3 to this. So this one is going to be 0, this is going to contribute 0, this is going to contribute 2 times 3. And then if there was another one here, it would contribute whatever it was times 9. Okay, so 6. And then this just goes over here, and this doesn't contribute anything that, okay. Wait, why don't we just do, let's just do 5, right? Let's just do 5, because that is what the sample input is, and let's see if our algorithm works for 5. Okay, and then this is going to be 0, this is going to be 0, this is going to be 2, and then this is going to be 3, and then we try to pull from over here, there's nothing, but we could just put our own 4 here. But then we also had to draw from here, so this would be 8. Oh, wait, what? Oh, hold up, we can only do prime numbers, I think. We can't do that. Okay, so we'll go to the next prime number. And this will give us 0, then 0, then pull this over, then pull this over, then pull this over. And then we had to take our 5, and then we had to add on our 6. So this would be 11. And then we can't go past that. So then it would be 11, and then we had to add 1 because we didn't count only ones yet. So then it would be 12, and is that the answer? Wait up. Oh, I feel like this is the right way to do it. Holy. How do you do this? Okay, let's see. Oh, we had to sum all these. And then we had to add 1. Okay, so 18, 20, 21. Okay, that makes so much more sense. So we had to sum this entire row because we could always add 1s after it. Okay. Oh, that's pretty good. Oh, maybe we could just put a 1 here, and then this carries over through all these. And then whenever instead of just randomly adding a 5, we could just multiply the 1 times 5 and add it. Oh, okay, so this whole row is going to be 1. Okay, I've done a really bad job at explaining what the heck I'm doing, but basically my formula that I figured out is like, oh wait, but that takes a long time to do though. Oh no, that'll take like log n time. So basically what you do is, at any point, you could take the one right next to it, or you could add in more 3s. So you could either take 1 3 above, or you could take 1 9 above, or whatever. Or wait, no, it's sum. So you had to take 3 and then 6. Wait, this doesn't work though, because it's gonna be way more than n squared time. Oh wait, can we just do It's like kind of like knapsack maybe. Wait, this is really knapsack, right? Okay, so it's kind of a knapsack thing. Okay, so we'll have our knapsack over here, and then if we only have 2s, we could, and then we have 0 1, then this is going to become 2, and then this is going to become 4, and then so on and so forth, and then, oh bro, knapsack doesn't work, because then it's like not ordered. I mean, it considers the different things ordered. Could we start in bar somehow? Oh bro, but that would be like n factorial time. Holy, hold up. Oh wait, you could use a modification of knapsack. So this is what I was doing is right. Okay. So basically we have 1, 2, 4, and then basically the number at the top is going to be your sum, and then the number to the below is like the sum of the k's that like have the sum above, if that makes any sense. So like, for example, if we had like, let's go to 6, okay? To sum to 6, you need 3 2s. So the k that corresponds to that would be 8. So we put 8 here. So right now we're only dealing with 2s, so let's go a little farther. we don't care about 3's yet. We haven't involved the next prime numbers yet. The only prime number we're dealing with so far is 2. Then once we get an 8, that's 4 2's. So in order to get that, we would have a product of 16. Okay, now we can actually bring in the other prime number. So for 3, we basically start from the beginning again, and we look at 0. And basically the 0 is 1, right? So if we multiply this by 3, our sum would increase by 3, but our product will be multiplied by 3. So this over here represents our product, or like it's a sum of like k's that multiply to 1, or basically it's a sum of the products that add to 0. So then in order to get 3 over here, we move it up 3 because the sum increases by 3 if we multiply by 3, and then the product gets multiplied by 3, so it would be 3 here. Then we go to here, this is 0 basically, so nothing changes, it doesn't change anything else. Then we go to 2, and we multiply 3 by 2, and then because it changes the sum by 3, our sum is 2, now it goes to 5. When we add in a 3, then this becomes 6 over here. Then we go here, do the same logic, this becomes 9, multiply it by 3, get 9, and then you add here, so this becomes 17. And then here, this becomes 12 over here, and then 18 over here, so 34. And that's all we got for 8. Okay, let us try 5 now. So we do the same thing, 0 to 5, multiply by 5, add 11 over here. Oh wait, we gotta do 4 first. Okay, we gotta do 4. Okay, so we'll do 4 first, so this would be an 8. Or actually, oh, this 1's annoying. Or maybe this should be a 0, but we always add 3 to the first 3. Yeah, honestly, this 1 doesn't really make sense. Huh. Oh, wait, no, yeah, that's because 2 is different from 4 itself. Okay, yeah, so this makes sense. So then we could put this over there, so it would be 8 now, and then the 2 goes to the 6, and then 2 times 4 is 8, so this becomes 25. Okay, let's just make sure that our 5 is right. So our answer to 5 should just be the sum of the rest of it. So 6 plus 11, wait, what? Hold up. Well, okay, you get the idea, but why is this not right? It should be 21 if we sum everything to the left. Did we do, oh, we didn't do 5 yet, that's why. Okay, never mind. Oh, the reason why is because 2 separately only gives you a 2. Oh, bro. Wait. It's not product. What am I doing? K is like your LCM, not your product. Ah, okay. Let's do this again. Okay, let's start from the beginning. So this won't work. Okay, because if you have 4 separate 4's, the LCM is still going to be 2. So in order to have like an LCM of in order to have an LCM of 8, you gotta have 8 in it somewhere. So we could just have 8. But then 8 times like anything else would work. 8 times 2 would work, 8 times 4 would work, 8 times 2 times 2 would work. Oh, why can't I think of this? I'm pretty sure this is the right approach though. So 4 times 2 would also give you 4. No, that sums to something more. Oh, huh. Okay, I guess for each one, like, just itself works for now. Okay. Because like the LCM of 6 with a bunch of 1's is going to be itself. Or sorry, like if you have k is equal to 6, then the way you would get to a sum of 6 would just be having 6 by itself, like a cycle of 6 things. Then you would have n is equal to 6, which is in the numerator, in the top, and then you'd have a k is equal to 6. So always for any n, itself works. Okay. Now if you multiply by a relatively prime number, or rather, if you multiply by a relatively prime number, it increases the sum by that much, and it multiplies the LCM by that much. Okay. But if you add in a not relatively prime number, then it doesn't change the LCM, but it changes the sum. But we only care about when it changes the LCM. Oh, okay, that makes sense. So I guess we do have to do it how we were doing it before, except I was just slightly off. Okay, so this is how it looks, and then we had to do 3's now. So 3, would put a 3 here, and then relatively prime, so we put 6 here, but this is not relatively prime, so that would not change anything. This is relatively prime, so we multiply by 3 and then add it to 7. So it would be 12. Okay, and we could go higher, but we don't need to. And then for 5, this would add 5 over here, so it would be 11. And then this one is relatively prime, so it would be adding to 7, 10, so it would be 22. And then 3 times 5, 15, add 15 over here, so it would be 23. And then multiply this by 5, and then it would be plus 20 or whatever is over here. But we're not doing that. Okay, so now we've gone through the prime number from 2 to 5, and that means we've covered everything for n is equal to 5. So essentially our sum is just going to be everything over here. So it would be 11 plus 7 plus 2 plus 1 is 21. Okay, and then for 6 it should also be 21. Okay, I think we finally got our solution. So basically you have to take all the relatively prime ones and then multiply them by the new prime. Well, you can multiply it by the new prime squared, the new prime cubed, and so on and so forth. So basically we have to go through this thing n times, so n, and then we have to go through like the log of the prime, because we had to go 3 squared, so on, so log n. And then we also have to go through all the primes that are less than it, so then that's also another log n. So that should just be, or no, root n. So this should be fast enough, right? So it's 10 to the 4, then some small number, and then 10 squared, so that should be plenty fast enough. Okay, let's do it. Holy, I don't know how to explain this well, dude, this is hard, holy. Okay, well, hopefully the coding makes it make more sense. Okay, repl.it. Okay, I don't think this problem is particularly hard to code, but like I'm just gonna do it in C++ because it's a gold problem and I do not want to screw this up. Okay, so exercise.in. All right, let's f-stream this boy. Okay, then we got an int n, and we got an int m, and then we got a read in both, and then we got to keep track of our dp. Wait, how did my relatively prime thing work? I don't think that makes sense. Or actually, so how did I decide which ones not to do? Oh, okay, so I guess we have to have two separate dp arrays so that we could consolidate them after, because we don't want to use the new values for like, so like when we're applying the 3 as a prime, right, we don't want to use this number and apply 3 again to it. So we want to keep it in a separate thing and then only look at the powers of 2, and then once we're done we'll add them together. Okay, so we'll have a dp2. Okay, so what we're going to do is we're going to go through all the prime numbers. Let's just have a real quick function to check if it's prime. It doesn't have to be too fancy. Okay, so that's just a real quick is prime function, and then we gotta loop through all the primes less than n. So I is equal to 2, I is less than n. Could it be less than or equal to? Yeah, it could be less than or equal to. And then if it's not prime, then we'll just break or continue. Okay, so we basically want dp0 to be 1, and then we gotta go through the powers of it. Okay, so let me just make my own power thing because like the built-in power is really slow, so we'll just do it our own way. Okay, so this is our fast power function, and then we just got to go. Wait, do we even need a fast power function? No, we don't, bruh. We don't even need a fast power function. Okay, and then we're gonna go through all the powers. So we'll do int j is equal to I, j is less than or equal to n, j times equals I. Okay, so now it's gonna be power of the I. Oh no, we first had to loop through the entire array. So for int k is equal to 0, k is less than n, k plus plus, and we want j plus k because that is where it's going to go. And then we'll set dp2, and then we'll do j plus k is equal to dpj times I, or no, times j, because that's that, and then this should just be k. Okay, and then at the very end we just want to see out the sum, so we'll have it run in total, and then we'll sum it from 0 to n. Oh, and then we had to consolidate everything into dp1 at the end. Okay, so dp I is equal to dpi plus dp2i, and then at the beginning we also want to set all of dp2 to 0. Oh, we can't do this k, we gotta have it k, and then here we do dpi, and then we just see out total. Let us test it. We'll have to do our mods at some point, but for now it should be fine for testing purposes. And that is not right. So let us look at our things. So we start with dp0 is 0, so this is 1, and then we have our other dp2 array. So we go to here, we find that 2 is a prime number, and then we go to here and we set all this to 0. Okay, so we set everything to 0, then we do dp j plus k. Our first j is going to be 2, so we set this to dpk, which is 0 times 2, so that's 2. and then we go to 4, we set this to 4, and that should be it. Okay, and then this gets consolidated in here. What's the problem? Let's see what our DP at the end is. Oh, the 4 doesn't happen. Oh, this has to be a plus equals. God damn. I mean, not that that matters. No, what? No. Well, yeah, it should be plus equals, but still. Oh, maybe, yeah, I guess that would be the problem. Let's see. Oh, okay, that makes more sense. Okay, let's do it. Let us test it out. Alrighty, C++11. Okay, moment of truth. Let's see this. Oh, wait, I didn't do the... Oh, well, that's not even close to right. Wait, let's think. I'm pretty sure I have the right idea, but like... it's not working on those. Let's see, what is the problem? Okay, let's test it for other things. Okay, so let's say 6, right? Then we get... all of our stuff should be the same, except 6, and then... oh, that should be 11. Yeah, I don't think there's anything new for 6, so let's see what happens if we put 6. 21, okay. Okay, let's try 7 then. So then, that's fine, and then 7, so this would be 12 over here. Okay, let's redo this. So this would be 12 if we take the 3 and then put a 4 on it, then 5, so this would be 22. Or, wait. Yeah. Oh, wait, what? No, that's right. What? I'm trolling. Wait. No, that should be fine. N squared, let's see. So 4, 4. Oh, so 6 should have something else. And we add 29 over here, so we add 7 to make that 29. So it should be 29 plus 21, so it should be 50. Well, so it's following our algorithm, right? But is our algorithm right? That is the question, and it clearly isn't. So let's see. Alright, maybe, okay, let us set everything to longs real quick, and let us do our modding everywhere. And then we'll mod equal everything. Okay, let us see. Okay, let's try it. I just added all the mod stuff. I think that's the problem. Because like integers do really weird cutoff stuff, so let's try that. Whoops, did I extract it? Alrighty, this is gonna be epic, I swear. Oh, okay, very nice. So I think the only thing that's problematic is our array, which is nice. Okay. Wait, that's pretty good. So our algorithm's working. We're just having a problem. I don't even know why I had a... oh, wait, no, we use it as prime. Holy moly, this is pretty good. But where do we get an error? How do we get an error? Should I just make these way bigger? Maybe? To make it bigger. Never hurts to make things big, right? Right? Hopefully. Or do I have a negative somewhere? No. Should be Gucci. Okay, please work, I beg. Come on, let's go. I have stuff to do. I don't have to look at your... oh, let us go. I think we did it. Yes! Yes, I know how to solve gold problems. Holy moly, this is crazy. This is crazy stuff. Actually, that was kind of satisfying, dang. Oh, but I don't think I explained myself well enough. I'm sorry, guys. Okay. Let me just go through the whole thing one more time. Just a real quick overview of what I thought. Okay, first observation. You basically find that there's a mapping between points, right? Now, the number of steps you had to take to get back to your original is the least common multiple of all of the different lengths of the cycle. That's because every 3, this cycle repeats, and every 2, this cycle repeats, so every 6, which is their LCM, the whole thing is going to repeat. Okay, so now that we got that, and we want to find all the Ks, which are basically the number of steps, we basically have to find ways to split up n. Because we know that, like, the sum of all the cycle lengths has to be n, because there's n nodes, right? And like there's an edge for every node. So essentially our problem reduces down into breaking up n into multiple parts so that these parts these parts LCM is k. Okay, so the only way to change your LCM is to multiply by a bigger power of 2, or by a bigger power of a prime. So the way we did that is we used a knapsack, and we basically started with powers of 2. So 1, 2, 4, 8, so on and so forth. Then we multiply these things by powers of 3. So this one could be multiplied by 1 power of 3, by 2 powers of 3, so it could be 3, it could be 9, etc. Then this 2 over here could be multiplied by multiple powers of 3 to get even more stuff, and then it could be multiplied by different powers of 5, and so on and so forth, and then you sum all of those together, and then you sum all of them this way, because if it's less, you just buffer it with a bunch of 1s. Like if you have 2 squared times 3 is equal to 12, if you wanted n to equal 13, just add in a bunch of 1s to the end, and then they sum to the thing that you want. Or that was a bad example. If you have 2 squared times 3 is equal to 12, so your k is 12, then your factors that you need to have are 4 and 3, so it's at least 7, but you could buffer it with as many 1s as you want. So you get 8, you get 9, you get 10. So that's why you sum all the way this way, because any n less than it can be buffered with 1s to get to the n that you want. Alrighty, I hope that was enjoyable. My first gold solve on this channel. I'm like kind of a mathy kind of guy, so this problem was not that bad. I don't know whether I'd be able to solve all gold problems if I just put it out there, but this was a success. Alrighty, that's all I got. Thank you guys for watching. As always, if you enjoyed the video, leave a like and subscribe for more. Let me know if you want more of these gold crash courses or any problems that you guys want or anything that you want. Really, I am open to suggestions. But other than that, thank you guys for watching again and see you guys next time.